Hello again. We left off talking about equivalent and equal sets and cardinality. In this lecture we're going to talk about infinite sets. But before we actually discuss individual infinite sets, I need to mention the concept of a power set. So if I take a set such as the one we used last time, set A containing 1, 2, 3, I can use these elements to list out the subsets of set A. So the subsets of set A are 1, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 3, as well as the empty set. Remember, the empty set is a subset of any set because if you superimpose the empty set on a set, it doesn't change the set. So this is considered a portion, a subset of set A. And if I now take all of these sets and consider each set a thing, an element, a member of a larger set, this is called the power set of A. So a power set is the set of all subsets of a set. The given set is A. Here is the power set of A, the set that contains a list of all the subsets of A. And normally we use a capital A for symbolic purposes. That's how you write the power set of A, P of A. Now, notice that I have 1, 2, 3, 4, 5, 6, 7, 8 members of this power set. So the cardinality of the power set of A is 8. So there are 8 subsets of a set that has 3 elements. Now let's make another set, set B. It only has 2 elements, 1 and 2. So if I try to create the power set of B, I would get set containing 1, 2, 1, 2, and the empty set. 4 elements in the power set of B. So the cardinality of the power set of B is 4. Okay, what if I shrink it down to 1 element? C has only 1 element. Power set of C, 1, and empty set. So the cardinality of the power set of C is 2. So what have we found here? We found that if the cardinality of A is 1, then the cardinality of the power set of A is 2. Right now I'm just using capital A to stand for any set. So if I have a set, whatever the element is, if there's 1 element in it, the cardinality of the power set is 2. Remember, this is also the number of subsets of A that I can create. If the cardinality of set A is 2, I can make 4 subsets. If the cardinality of A is 3, I can make 8. And I didn't do 4, but by now you should see there's a pattern forming. And if I had written out all the subsets of a set containing 4 elements, I would have had 16. And 5, I would have had 32. And 10, I would have had to list out 1,024 subsets. And I know that because these numbers are not just double the previous number, they're actually powers of 2. Sorry. And I happen to know 2 to the 10th is 1,024. So, in general, so to sum up, or in general, the number of subsets equals 2 to the n, where n is the cardinality of the set. So you just take the cardinality of the set, take 2 and raise it to that power, and that's how many subsets you can make from that set. And it's also true, and this point will become important in a minute, that 2 to the n is always bigger than n, assuming n is positive, which, since it's a cardinality, it will be in this case. Okay, so now we're going to talk about infinite sets. So we're going to start with the very simple infinite set of natural numbers. Abbreviated capital N. The natural numbers are simply the counting numbers, so 1, 2, 3, 4, 5, and so on. So there are an infinite number of these counting numbers. There is, of course, no end to this set. However, even though there is no end, I can write out the first few elements of this set in an orderly fashion, so that when you see 1, 2, 3, 4, 5, ... you know exactly what set I'm talking about. You know that this pattern is going to continue. So I could cover up the capital N, and if you had just looked at this, you would know what set I'm talking about. And you would know it's infinite because of the ... Now, the question before us is, what is the cardinality of n? Well, it's infinite, so maybe it has no cardinality. But even if it had no cardinality, you could at least call n countable. You may not be able to get to the last number when you're counting, but you can put the elements in a particular order so that you can start the action of counting. You can start the counting process. And you have the choice to stop the counting process at any point in time. But at least you can count. So this set is considered countable because you can put the elements in a logical order, and the order that you choose ensures that you will not skip any elements. Okay, I made sure to add 1 to the previous element to make sure I didn't skip any. Now, even though the quantity of this set is not a numerical value that you would find on the number line, there actually is a cardinality for the natural numbers. It's not a real number. You can't find it on the number line. It's a made-up number. And the purpose of this number is one thing. It's to represent the cardinality of the natural numbers. So I'm going to take off the question mark. And I'm going to state that the cardinality of n is this weird-looking symbol. This symbol is called Aleph null. And it stands for the cardinality of the natural numbers. It is not a real number, of course. Okay, now that we have the cardinality of n, I want you to think about how many subsets of n are there? How many subsets? Well, you obviously can't list them, but you can say that the cardinality of the power set of n would be 2 to the Aleph null, which is bigger than Aleph null. It has to be bigger. Think about it. You are raising 2 to this power, and this power itself is an infinite number. You are raising 2 to an infinite value. Whatever that is has to be on another level. It has to be bigger than Aleph null. Now let's say we have the power set of n. I don't know what's inside the power set of n, but there are a bunch of sets in the power set of n, and it's infinite. How many subsets are there of this set, the power set of n? Well, first, the cardinality of this is 2 to the Aleph null. So that must mean that the cardinality of the power set of n is 2 to the this thing, 2 to the Aleph null. And that has to be bigger than 2 to the Aleph null. It has to be on another level. So not only did I find a second level of infinity when I found the power set of n, now that I've looked for the power set of n, I found a third level. And there's nothing to stop me from asking the next logical question. What is the cardinality of the power set of the power set of the power set of n? Well, it's going to be 2 to the 2 to the 2 to the Aleph null. And that is going to be bigger than 2 to the 2 to the Aleph null. And I could conceivably do this forever and ever, each time creating a new level of infinity. So, theoretically, because of the formula for number of subsets, 2 to the n, and because the exponent that I'm raising 2 to, in this case, is infinite, I can create more and more levels of infinity as many times as I want. So theoretically, there are an infinite number of levels of infinity. In which case, that means that there are quantities that will never ever be discovered. I should say never, but it's likely that there are quantities that will never be discovered by mathematicians. And I would even venture to say that it's likely that whatever math we do know at the moment is a very small part of all the math that is out there. But for our purposes today, because we are going to talk about other infinite sets, just remember, if you remember anything, remember two things. The cardinality of the natural numbers is Aleph null. It is countable. Cardinality of natural numbers is Aleph null, and it is countable. Now, the holes. abbreviated W, contain 0, 1, 2, 3, 4, dot, dot, dot. What is the cardinality of the wholes? Is it the same as naturals or different? And if it's different, are there fewer wholes or more wholes? Well, you can see that the naturals start with 1, and without the 0, we have the naturals staring at us. Wholes has 0. So does that mean wholes has more? Some people say yes. I would say no. If I write the naturals directly underneath the wholes, and I do my one-to-one correspondence pairing off process, I can pair off the 0 with the 1 with the 2, the 2 with the 3, the 3 with the 4, and the 4 with the 5. And if you think ahead, I can do this forever. And as long as I pair off in this manner, there will never be a leftover element in either the whole set or the naturals set. Never be a leftover. Won't be an extra. So if the cardinality of naturals is Aleph null, and wholes I can put into one-to-one correspondence with naturals, then the cardinality of wholes must also be Aleph null. So they are the same cardinality, they are equivalent sets. Now on to integers. Sorry, these are integers. Now integers are kind of interesting because you have positives and negatives, and you have also 0, which has no sign. Well, I can't, when I'm listing out elements in a set to check their cardinality, I can't go like this, because I'm not allowed to have dots in both directions, because I want to minimize the number, I want to limit my set to going in one direction. Dot, dot, dots on the right. Because my objective is to do one-to-one correspondence. I can't do that if I have dots on the left also. So this kind of listing, this way of listing the integers won't work. But if I do this, I will be able to list out every integer without skipping any. And I'm only going in one direction. I'm just going to the right. Now, I place naturals underneath. Do I have one-to-one correspondence? Yes. Pairing off works. So, the cardinality of integers, also Aleph null. So far we have not found another level of infinity, the theoretical levels of infinity that I mentioned here. Okay, let's keep looking. Rationals, abbreviated Q. Rationals are fractions, which includes decimals, percentages, because all of those can be written as fractions, right? So we're talking 1/2, -2/3, 5/2. Whole numbers can be written as fractions, so whole numbers are included. Any integer is included, and so on. Now this is rather hard. How do you list rationals without skipping any? So I'm going to leave this matter of listing it out for class time. But I'm going to sort of give you the punchline that rationals can be listed in a logical manner without skipping any. This is obviously not the list. And therefore, rationals also have the same cardinality as naturals, Aleph null. Now, irrationals, abbreviated I, include square roots of non-perfect squares like square root of 2, square root of 3, pi, e, what are known as transcendental irrationals, and so on. You may know irrationals as numbers if you wrote them as a decimal, would go on forever, but they don't have a pattern. So, what is the cardinality of rationals? That'll be the subject of the next video. See you then.